Let's see one question that was asked in gate 93. Okay. So this was asked in gate 93. So this Cayley-Hamilton theorem has been asked in gate sometimes directly, but at least 4 to 5 times I could see that it has been asked, and that's why I'm adding it in our lecture. So let's see what it says. So they say that let A be a n cross n matrix, right? And because we are discussing about eigenvalues and eigenvectors, we know that the matrices that we are going to work with are n cross n. So they're saying that if lambda power n, c minus n minus 1, c n minus 1, some constant lambda power n minus 1, blah, blah, blah. Basically, this is the characteristic equation, right? Characteristic polynomial. So we also call it characteristic equation. If it's there, then the matrix A will also satisfy that equation. Okay. So what we know that when we find the characteristic polynomial, we know that if it's a n cross n matrix, then lambda power n plus some constant, right? Cn minus 1, lambda n minus 1, blah, 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 and C0, right? It is 0, right? This is the characteristic equation. What Cayley-Hamilton theorem says is that if instead of lambda, you put matrix A, for which we had the characteristic polynomial, then the equation will satisfy it. It means that A power n plus Cn minus 1, A power n minus 1 dot 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 C0 will add up to a 0 matrix. Okay. So it's just a statement. You can definitely, I will suggest you please go and verify this. I will not do the verification here, but we'll do some questions on this. Verification, please try to verify this. Okay. So all it's saying is, for example, suppose there is a matrix A, right? And I am given that this is the characteristic polynomial for this. Okay. So if I do A square minus 2A plus 1 will be identity, then it will give me 0 matrix. This is all this is saying. Fine. Any doubts here? This any doubts? Any questions? Fine. So this is just a simple theorem. The proof is in the handout. If you want to go through it, you can check out the proof. Okay. Okay. Now this is the second part of the theorem. It says that, so this is actually a continuation of this. So this is the second part. Okay. So it says that if you have a matrix again, a n cross n matrix with some lambdas and their multiplicity is also included. So it means that lambda 1 can be equal to lambda 2. Right? So I have listed down all the eigenvalues, right? So what they're saying is if I do some g of x, or I have a polynomial which is like a g of x such that it's a k power polynomial, and I apply that same polynomial to my matrix A. Okay. Then what happens to suppose I had a polynomial g x is equals to x square plus 1. Okay. I am applying the same polynomial to A, which is A square plus 1. Okay. So what it's saying is that the eigenvalues of GA are basically to each lambda, you will apply the same function. Okay. So if my lambda values were lambda 1, lambda 2, lambda n, then my values will become, so this will become lambda square plus 1, lambda 1 square plus 1. This will become lambda 2 square plus 1, etc. Lambda n square plus 1. Okay. Okay. Now there are some corollaries to this. Okay. So again, it's saying that A is an n cross n matrix and you have some n eigenvalues, and obviously they can repeat. Then 2A will have eigenvalues 2 lambda 1, 2 lambda 2, 2 lambda n, right? A square will have squares. A plus 2i will have lambda I plus 2. And if P lambda is a characteristic polynomial of A, then PA will have eigenvalues 0, 0, 0. Okay? Okay, this, let's look at it. I have not looked at it, but let me see if this is true. So if this is a characteristic polynomial, so it's saying lambda square plus 2 lambda minus, say, 2 is equals to 0, then P of A will be lambda square A square plus 2A minus A, right? It's a zero matrix. Then P has, then this has, oh, basically because this is a zero matrix will have all the eigenvalues as 0, 0, 0, right? Fine. Make sense? Now, I will copy to a new slide. So, triangular matrix, right? Upper triangular matrix. Upper triangular matrix, right? So, eigenvalues are, what are the eigenvalues? Okay. Okay, minus I, right? So what means, so this is lambda minus 1. So my characteristic polynomial is this, right? Lambda plus 1. Then lambda minus I and lambda plus I, right? This is my characteristic polynomial. So I can combine this. So now I can use Cayley-Hamilton theorem. Or I'll just call CH theorem. So I can, so this is equals to 0, right? So I will do or let me compute this later, right? So I will have, so I can write it as lambda square minus 1, right? And I can write it as lambda square. So minus I whole square is equals to positive 1, right? So this is lambda square minus I square. So this is lambda square plus 1, right? Now I can again combine these two. So it is A minus B. So I'm using A. I'll just write this property here. A minus B, A plus B is equals to A square minus B square. Fine. Now I'm going to do the same thing. So this is lambda power 4 minus 1 is equals to 0, right? So lambda power 4 is equals to 1. Now let me use CH theorem here. Using CH theorem. I know A power 4 is equals to I. Fine. 1 is basically I, right? So the answer is I. Fine. Yes, no. Okay. 1 yes. Cool. Now let's do another question that was asked in EE in 2008, and it's also a PYQ. So now they have given you the characteristic equation, the characteristic polynomial for a 3 cross 3 matrix. Okay, and it is given here. This is the 3 cross 3 matrix ka polynomial, right? Now they are asking you that what will be the P inverse. Okay, so you have to find P inverse, right? So here also we'll try to use Cayley-Hamilton theorem. Okay, so let me see how I can use Cayley-Hamilton theorem. So I know that lambda 3 plus 2 lambda plus lambda square plus 1 is equals to 0. Okay, right? So let me put this PQ plus 2P plus P square plus 1 is equals to 0. correct? Now I can do is, let me multiply with P inverse on both sides. PQ plus 2P, because I want to make a P inverse. I don't have it, so I'll try to make it. Okay. Now P inverse into P cube is basically P square. Okay. So 2P and this will be 2 and this will be P plus P inverse is equals to 0. So what will I have? So this will be basically negative of this term, right? So minus P square plus P plus 2I, right? So this is the correct answer. Fine. So this is the answer, right? So D is the answer. Fine. So